ready for takeoff.
I guess we can go ahead and get started. What's up, everybody? Post lunch, I will try to keep everybody awake, I guess. But yeah, what's going on, everyone? I'm Ryan. I am one of the maintainers of a library called Pyroscope, and today I'm going to talk about continuous profiling, about Flamegraphs, particularly in Ruby. I don't know if anybody happened to have been here last year or I guess at RubyConf last year. I believe her name was Jade Dickinson, gave a talk about profiling and Flamegraphs. That was really good, and that's kind of where I got sort of the basis of this talk from. I thought she did a really good job, but when you're using Flamegraphs in in some ways, it kind of tells part of the story, and I think adding kind of continuous profiling as opposed to normal profiling, which I will explain what the difference is in a little bit, it kind of tells a little bit more of a story, and so I'll give some examples of that in the end. Real quick of what we'll go through, just what are Flamegraphs in general, the different types of profilers, how to go from normal profiling to continuous profiling, and then how to manage the storage, and then some examples of how you can use them to help tell a story for your application or whatever you want to tell a story about. So there is no better place to start when talking about Flamegraphs than a illustration by Julia Evans, who is, as many of you know, pretty popular in the Ruby community. And this is a illustration she made, sort of just explaining in the abstract how Flamegraphs work. And so for those who aren't familiar, basically I'll show a less abstract version in a second, but basically how it works is that you sort of start with a application and some sort of metric. In this case, we don't know what the metric is, but on the base where you see main, that represents 100% of the time that this application was running. And then you can kind of think of these Flamegraphs as like a tree. And so in this case, main calls both alligator and panda, which then, work on something for 60% and 40% of the time respectively. And then alligator calls bite and teeth, panda calls bamboo, so on and so forth. And basically the way that you sort of use this is it kind of helps you understand whatever metric you're looking at to be able to see sort of where you want to optimize resource utilization, whether that be CPU or memory or some other type of metric, or maybe there's something that happened on a server and you want to understand that. But whatever it is, this kind of gives you honestly like a nested pie chart, or like a pie chart on steroids of what your application is doing and where you should look if something is wrong, or if you do want to improve performance or something along those lines. She also, I believe, references Brendan Gregg in here. He also, one of the sort of pioneers of using this sort of technology at Netflix, I believe, and other places. And so, here's a less abstract version with kind of a code example on the right. And so this is how this very, very basic example would get turned into the Flamegraph on the left. So you see while true, then you see fast function and slow function, which each call work, and work runs for 2 units of time and 8 units of time respectively. These numbers are usually represented in samples, and so so this is what it would look like with a real piece of code broken down into a Flamegraph. All right, and so I mentioned that I'd talk a little bit about the different kinds of profilers, and so there's really 2 main types that that are popular. One is sort of the for lack of a better term, call it the standard profilers, and that's basically they're sort of instrumented inside the classes or the methods to report when they run. So you can kind of think of those as sort of like breakpoints that you would put at the beginning and the end of every function that would then sort of break it down, and you would say this function started at this time, ended at this time, this function called this function, and so you sort of have a breakdown that way. And so yeah, that's a very accurate way to get profiling data and to understand when applications are running and how they're running. And so that's on the beneficial side. On the downside, if something does go wrong, it is slightly less, or I guess depending on how many functions you have or how you're using it, less performant and more likely to break or hang or something if something did go wrong and and you didn't catch it properly. The alternative to standard profilers is sampling profilers, and that's something that's become much more popular more recently, as a lot of people are sort of shifting particularly to a continuous profiling sort of model. And the way that works is a little bit differently in that rather than having to instrument your code with all these different breakpoints or have it automated through some library in that way, the way sampling profilers get this data is they sort of from outside of your application sample the stack trace at a certain frequency. So a common one is 100 times per second. And so it's going to look at the stack trace a bunch of time, send all of that information somewhere else, and basically that's how it figures out what was being called and what was being worked on at any given time. And so that is obviously slightly less accurate because it's going to be, of course, sampling. But at the same time, you can sample so frequently that it, sort of the benefits definitely outweigh the costs most of the time, and that you can still get a pretty accurate, depiction of what was going on in your application for all intensive purposes. But you do it without the performance hit, and it allows you to get a lot of profiling data that you can then use however you'd like. Okay, so yeah, so there's a number of different profilers, as particularly in the Ruby community. You may have seen or used some of these: rbspy, stackprof, rack mini profiler, app profiler are all popular ones that a lot of people use for various different use cases. There's a good article that someone from Shopify wrote that kind of like breaks down all of these. I'll, I guess maybe at the end of this, put up the link if you want to look at the notes at the bottom and check that out. But yeah, they're all kind of used for different use cases. But most frequently they're not used, or at least out of the box, they're not necessarily meant for continuous profiling. They're meant more for, you want to SSH into a server, figure out why it's acting weird, and you might, run rbspy to figure out, what's going on, or, what your application is doing, something along those lines, or maybe, during a test suite or something, or a script. So they're typically used in more of an ad hoc way, as opposed to constantly profiling your application, just because, if you are constantly profiling your application, you then have to make some kind of sense of all of that profiling data. And, so a lot of people who are using these will use them in sort of more ways where they, are looking specifically at a specific time period or a specific server or something along those lines. But what Pyroscope does, and what we'll talk a little bit more about as this talk goes on, is basically taking data from any of these profilers. In Pyroscope's case, it's the client uses rbspy, but taking any of these profilers and then sort of like sending them to an external server that will then allow you to basically, without having to tell your application when to profile itself or having to actively profile your application when you want to see something, this profiles it all the time, and then you can use Pyroscope to basically query it, think like Prometheus or something like that, where you can go in and make sense of the data in retrospect, as opposed to having to sort of predict when something's going to go wrong and have the profiles that way. And so how Pyroscope works is then, yeah, taking these profilers, basically using a component called a session manager that will then determine how often to collect the profiles, turn the profiles into some sort of standardized format, and then send those profiles to the Pyroscope server where a bunch of compression and efficiency operations are done to make it so that you can both store the data efficiently and then query the data back efficiently. And so that's sort of, again, the difference between sort of just like static profiling or ad hoc profiling and then continuous profiling is this concept of putting it somewhere where it can then be queried and used sort of retroactively, without having to do anything extra. And yeah, this is just like a little bit more, I guess, in the weeds details of how we did it. It definitely gets pretty complicated and has taken a lot of different iterations. But basically, we wanted there to be sort of like two options. One where you can sort of profile your application without having to do anything, but also sometimes there is that concept of like a breakpoint, or in this case we call it a tag, where you want to be able to sort of organize your profiles in some way that's meaningful to you. So in a Ruby context, that might be getting a profile per controller or per action, or something along those lines, so that you can sort of see later a breakdown of why a particular controller was acting in a certain way, or action, or whatever it might be. And so in order to enable that, there's sort of two pieces to it. One is the in the Ruby application, you add the gem, and you can use this tag wrapper to basically wrap any code that you are particularly interested in seeing. And then we have the Ruby gem itself, obviously, which then basically just wraps rbspy on top of that, and effectively just like adds metadata to the profiles that rbspy is collecting. And then, as mentioned before, then storing it in a way where you can then query based off of that metadata, or at a high-level view, just seeing the whole profile itself, without breaking it down. Yeah. Okay. So yeah, this is kind of what Pyroscope looks like. A little bit different than than profiles that many might be familiar with. And yeah, this is kind of just breaking down the UI is a little bit different than a lot of profilers that people are familiar with. I know, yeah, typically when a lot of people think of Flamegraphs, they kind of think of these, more fire-colored ones. And this one's a little bit different in that it, let me go back to showing the slideshow. This one is a little bit different in that, there's like a little bit more kind of method to, the coloring. It's colored by package in this case. Also adding a table view to be able to understand sort of, what's going on there. And then, in this case, this is profiling CPU. And so this top graph might be something that you would otherwise get from, like Prometheus or something along those lines. But this sort of like, kind of combines all of this information into one view, where you can then sort of zoom in, and I'll go through a sort of live example in a little bit, but sort of zoom in and understand kind of different subsets of the application. And then, as I mentioned before, there's sort of this tag bar here where you can then see sort of, if you wanted to see by controller or action or that kind of thing. And yeah, and so that's one thing that we sort of built on top of. We added in, took a lot of inspiration from like Speedscope. If you've also used Speedscope, they have a really great UI as well. And so we sort of just built on top of a lot of what a lot of other tools had done in sort of various different packages, and then tried to combine it all into one convenient package where you can use it all together. So for those last 2 points, for the high cardinality and the queryability, anytime you talk about that, you run into this sort of issue of, with high cardinality data or data that you want to query, how do you store it efficiently and how do you query it efficiently? And so I'll talk through this briefly on what Pyroscope does to sort of like solve that problem of like, as you can imagine, profiling data is pretty large. Profiles can be really big, there can be really long stacks, and if you're storing those at any sort of frequency, it can start to add up really quickly in a way where it sort of offsets whatever performance improvements that you make if it's then too expensive to get the data. And so, the first problem that we solved was sort of the storage requirements aspect of it. And that basically, as you can imagine, stack traces have a lot of repeated data. And so by turning them into trees, we found ways to actually, implement a lot of the sort of, like algorithm, basics that you learn sort of as you're learning a lot of languages like Ruby or whatever, in order to compress the data using trees and get rid of a lot of that duplication in the stack traces themselves. So yeah, in this case, combining these so that you don't have to say the same, file name, for example, multiple times when it's in every stack. And then basically, kind of then going even further, the symbol names themselves have a lot of, can have a lot of repetition. And so basically by serializing the symbol names and sort of like storing a dictionary, you can turn, net/http.request into just, in this case, 00, which is obviously much more efficient to store that than to store this, these long strings for the symbol names. And this, compresses things even further, giving room for that high cardinality data and, data that you want to be able to query later. Okay, so that's, on the storage side, how we store it really efficiently. And then the question becomes like, once you have all this data and it's stored very efficiently, how do you get it back in a way that's, both fast and, somewhat efficient? And so the way we did that was using something called segment trees. And basically what we do is Pyroscope sort of uses rbspy to collect data every, in 10-second sort of chunks, and then it sends it to the server, right? And so if you want to look at, a day's worth of data, it would have to merge, a lot of 10-second chunks that make up that day, right? And so what we did was, is instead of storing those chunks in solely 10-second chunks, we then basically aggregate them at different granularities so that, basically when you want to query them back, it's more efficient than having to merge, however many 10-second chunks are in a 24-hour or a week-long or a year-long period. And this makes it a much more efficient operation. Here's kind of a depiction of that. So in this case, if you wanted to get 50 seconds worth of data, if we didn't do anything special, you would have to then do 4 merge operations, which will add up over time if it was a 5,000 or 5 million second query range. And instead, with this, you're able to then get one 40-second block and add a 10-second block, as opposed to merging 5 10-second blocks together. And it just makes things much more efficient, and again, makes it possible to be able to then be as efficient as possible at its core, so that you can then break things down in in a more high cardinality way later. And so here's just some stats that I found of like other companies. Profiling is also often associated pretty closely with latency, and so companies like Amazon, Google, Uber, you can imagine there's for every millisecond in latency, particularly when you're at that kind of scale, it can definitely make it so that you're losing revenue. People are either churning or leaving your website. In the case of Amazon, they claim that they lose $1 billion in revenue, and this was a while back. They're probably even more now. Google, same thing. The longer it takes, the less likely people are to visit a website. I'm sure everyone here who has used Uber and Lyft, when one's taking long, you switch to the other, vice versa. And so profiling sort of helps break down that that time period of like, why is this application, why is this particular request taking so long to load, or something like that. You can then use profiling to sort of break that down and understand it. and improve, it's sort of like the business case for profiling for Mini. So yeah, now I will, in the time left, go through like a couple examples. The first one I'll go through is just sort of like a real world example, but that sort of just shows kind of what I was talking about with the ability to understand like tags and to break down profiles. I'll show with a Ruby application. Basically, just think it's like a simple, rideshare application. There's 3 routes, one for car, one for bike, one for scooter, and we tag those as vehicle. And then there's 3 regions, and we tag that as region. And this is what we end up with. Let's see. Hopefully, this will be big enough that you all can see it. Yeah, so I guess, yeah, so I'll start from like the top piece. And so as I mentioned, the ability to tag things is one of the, let me make it a little bit bigger. The ability to tag things is one of the really important enhancements that we made over rbspy. And in this case, now you could break things out by action. And you could see, scooter/index, car/index, bike/index, and a pie chart of sort of like the CPU utilization. And, in this case, if you were trying to debug this, you might want to say, okay, why do cars take 60% of the total CPU for this application, whereas, bikes and scooters take significantly less? And then what Pyroscope allows you to do is kind of then now you can select each one of these individually. And it's kind of hard to see because the stack is so big, but this profile changes based off of whichever one you're looking at. And so in this case, let's say we were looking at region, and there's, you see one region is taking a particularly long time. What Pyroscope allows you to do is sort of, jump in and see like this. I'll compare. This region that's consuming 50% of the time with another one that's consuming much less. And then what you end up with is this flame graph here, which is very tall. Let me collapse it so it'll be easier to see. And so you get this like diff flame graph that basically takes the 2 of those flame graphs and shows you what is the difference, kind of like think a code diff. What is the difference between flame graph A and flame graph B? In this case, you would be able to then kind of see that the baseline, which is the first one, has 60% CPU utilization. The second one has 14% for this particular function. So maybe it's, I guess in this case, it's check driver availability. This would be representative of, maybe looking for a driver is just taking much longer for one region than it is for the other. I don't know, maybe there's a sporting event or something that's going on. But, if you were debugging this issue, profiling would help you sort of understand that and figure out, what's special about one region versus another region. And as I said, here's how you would then, query those different tags separately. All right. Another example, this is one that we got from, or one that we sort of added, a view that we added that is pretty popular in speedscope, is this view called sandwich view. So if I go to another application, where is it? Okay, yeah, so if I go to another application, this one, it basically, if you're looking at the regular flame graph view, you might not actually, here, let me see this. You might not actually tell, sort of see certain functions that are really common here. So there's a lot of, something like logging you can imagine gets spread out through a lot of different code paths. And so another thing that's pretty nice from here is that if you, select, so in this case, if we select logging and we're looking at the regular flame graph, you can see little, these little pink pieces are areas where logging is getting called. And often we see, this can, in this case, it's only taking, 6% of total CPU, but sometimes that can be a lot depending on how much logging you're doing. And so another way that you can sort of use this is to understand in sandwich view seeing sort of these are all of the functions that are calling logging, and then these are all the functions that logging then calls as children. And so this kind of helps you then break down kind of, those functions that are spread out a lot across the code base. Sometimes the best performance impact that you can make is looking at those functions and understanding sort of why are they taking so long. Maybe we should be doing less logging. Maybe we're sending those logs off somewhere and not using them, something along those lines. And the last example that I will give is one that is somewhat near to our hearts. It's so this is actually what me and one of the other maintainers who's sitting up here, Dimitri, what sort of gave us the idea for Pyroscope. We were working at a company that was using Ruby, and basically we were using, I don't know if anybody's used the Brotli package. I think that's how you pronounce it. And we were using that to do some compression. And we kind of were just going through a round of performance optimizations for our application. And so this is before we had Pyroscope to use, and we were just using rbspy sort of in a more ad hoc way. But basically, we were able to sort of use it to figure out. So by default, if you just compress a response using Brotli like this, it by default is set to the maximum level of compression, which is 11, or just the number 11. And basically, if you then, if you don't know that and you're looking at the application Flamegraph, I've got too many tags open here. So we kind of just like A/B tested it basically to see, okay, what's the difference? And so we kind of did we did one at 11, compression and one at 2 compression. And we were able to see pretty quickly that the, default level of compression consumes significantly more CPU utilization, that's this yellow piece, than the other one. And when we did the diff between the two, do the diff again. We were basically able to kind of, at first we sort of looked at the initial flame graph itself, but basically as we kind of dug deeper, we were able to find that that the problem was that this big chunk at the bottom was basically this compressed response function. And in our case, I think it saved like roughly 30% of CPU. We were able to scale down a bunch of servers that we were needing to do all of this work. And it was just because we had no idea that this Brotli function was by default set to the maximum level of compression. And the only way we were able to find that was then, again, by just like going into this view and being able to see, we kind of scroll down to the bottom and we see, okay, why is this piece of the flame graph taking 72% of the time? And, again, that was because of the compression thing. And so often it's, logging, compression, serialization and deserialization, something along those lines. But yeah, basically, you kind of start with looking at a flame graph like this. You can make a change and then use continuous profiling to sort of compare the before and after, which tells a story, hopefully, of how you improved performance for your application, but is, in the end, pretty useful for understanding why performance issues are happening and how you might be able to fix them. So let me see. I believe that is everything. We've got a couple more minutes. Happy to answer any questions if anybody has any. But otherwise, thanks for coming and listening to the talk, and have a good rest of your conference. Yeah, that's a good question. So the question was, sometimes, with the example here, maybe you are, maybe you did something, maybe something actually did change in your application, and you want to be able to do that. One thing that, we use it a lot internally, obviously, dog fooding it. One thing that we often do is we add a tag for like commit, and so you can see, basically what version your code was on between, between flame graphs, and or add that into here. So that can sometimes change. But Yeah, I mean, typically you're going to have to use this with, some other tool probably to like help, and it does take some sort of knowledge of what's going on in your application. Maybe CPU increased because, it's like holiday season and a lot of people are like buying things or something like that. But oftentimes you kind of, in the real world, it'll be like, like a spike in CPU or something where you're like, that seems fishy, and then you kind of dig in a little bit further. So it sort of depends case to case, but basically, again, using tags, you can kind of help to weed out some of your like hypotheses on why it might have changed, but otherwise, it kind of helps to just be able to dig down and figure out, does it look normal to you, or is it something that's kind of special? Yeah, so we use Sidekick a lot. Again, this is a demo one, so I can't show the actual code. But so the way we do it is we just set those up as, in our case, 2 separate applications. But same way here, you kind of have the Pyroscope server itself, and then the rideshare application. But sorry, I should repeat the question. I don't know if this is still on, but the question was like Sidekick and other other things that might be running sort of not in the same place or whatever. How does that work? And so you can just do the exact same thing. You would just set up a different application name, and then you can break it down. Or if you really wanted to, you could send it to the same application and just use a tag for the Sidekick job. But this is actually really convenient for debugging Sidekick workers and why they are notoriously hard to deal with. Yeah, so the question was for this example where we were looking at the compression thing, and there was, we were able to see high versus low. In this case, the way I set up this example was more of like an A/B test type of situation where they're both running at the same time. When we did it actually, in practice, we sort of did it, you could also do it, for example, like staging server versus a regular server. So you might like, compare, like using a load testing tool, for example. That's like another way that you can test it. If you test in production, you could just push the change and see, how the metrics change, and sort of instead of seeing, these 2 lines running at the same time, you could show 1 line and then compare before and after versus comparing them at the same time, at different levels. That's another way you can do it. But All right, thanks again, everyone, and have a good rest of your conference.